Section 3.4 relates physical properties to intermolecular forces. So we'll start with boiling point. So remind yourself, of course, what a boiling point is. It's the temperature when liquid goes to a gas. But there are other ways of thinking about it as well. So the question that I would have is, what has to happen to go from a liquid to a gas? The answer to that is that to do so, you must break all intermolecular forces. So if we have stronger intermolecular forces, they'll be harder to break. Therefore, your molecule will have a higher boiling point. So if I want to see how the different intermolecular forces affect the boiling point, I can take three molecules that have similar molecular weights and examine first what their boiling points are, then we'll talk about why. So pentane is 36 degrees C, butanal 76 degrees C, and butanol 118 degrees C. So my question for you is why? So I would pause the video, try to see if you can explain with intermolecular forces this change in boiling points. If I'm going to start trying to analyze this question, the first thing I need to do is go through each molecule and try and figure out which intermolecular forces they have. So all things have van der Waals forces, so I would start by writing van der Waals on all three. The second molecule has dipole-dipole interactions, because this carbon-oxygen bond here is polarized. Delta plus on carbon, delta minus on oxygen, so that makes a dipole. Here I've got all carbon and hydrogen, so I don't have any dipoles. And this last one has dipole-dipole again. The carbon-oxygen bond is a dipole. But it also has something the other one didn't, and that's an OH, which has hydrogen bonding. As I go from van der Waals to van der Waals plus dipole-dipole, my boiling point went up about 40 degrees. As I went from van der Waals and dipole-dipole to all three, it went up about 40 degrees again. What that's saying is that hydrogen bonding is by far the strongest of the three, yet dipole-dipole is much stronger than van der Waals forces. Van der Waals forces are by far the weakest of the three. Now, a melting point, of course, is when you go from a solid to a liquid. But another way to think of a melting point, we need to overcome the forces that are keeping a crystalline solid ordered. And while the trend is the same, stronger intermolecular forces yield a higher melting point. It's not nearly as dramatic. So let's take the same exact molecules. So if I have pentane, it's minus 130 degrees C. Butanal, minus 96 degrees C. And butanol, minus 90 degrees C. What about solubility? The solubility rules that you learned in Gen Chem are pretty much the same solubility rules that we'll use in organic. And the main solubility rule is like dissolves like. Which means that polar solvents dissolve polar compounds, while nonpolar solvents dissolve nonpolar compounds. So ionic compounds, which are highly polar, typically are going to be water soluble, but often are organic insoluble. While organic compounds are soluble in most organic solvents, but are only soluble in water if they have hydrogen bonding groups on them. Typically, there are some small molecules that are soluble in water still. And so typically you want at least one polar group for each 5 carbons. So let's look at a couple examples of our solubility. So here's the molecule butane. Butane would be organic soluble, but water insoluble. Why? Because there are no hydrogen bonding groups on there. So there's no polar groups, so there's no affinity for this in water. What about alcohol? This would be soluble both in organics and water. Okay, so I'm going to draw a couple larger molecules, and you can tell me whether you think they should be soluble in water or not. Okay, these are our 2 molecules. So the first one, we have a whole bunch of carbons, and we've got 1 hydrogen bonding group out here. So this one should be water insoluble. This one, I've got 1, 2, 3, 4, 5, 6 carbons, but if you look, everywhere I look, I've got hydrogen bonding groups, I've got polar groups, so this one should be water soluble. This first one is vitamin A, so it's a water insoluble vitamin. Versus the second one, which is vitamin C, which is a water-soluble vitamin. And this is important because if we take in excess vitamin C, we just excrete it and we get rid of it if we take in excess. So it's not a problem. However, if we take in excess vitamin A, since it's not water-soluble, it doesn't get excreted as easily. And if we take in excess, it gets stored in fat cells. And primarily in the liver.